We continue our study of vectors by moving into space. That is, we will now look at three-dimensional coordinate. So the two-dimensional coordinate system, recall, consists of two perpendicular axes, a horizontal and a vertical. A three-dimensional coordinate system can be formed by adding a third axis to the two-dimensional system that is perpendicular to both the horizontal and vertical axes, as such here. So we have a vertical, we have a horizontal, we add a third that is perpendicular to both. Now it's hard to see, but this third axis actually is coming out of the page. So this is coming out at you. Now by convention, we set this axis, the new axis, as x. We shall call this the depth axis. This y-axis is the horizontal, and the z-axis will represent height. Now this is not particularly set in stone, as long as the axes follow a particular rule, which we'll look at on the next slide. However, for this course, we will be using this convention setup. We'll use x is depth, y is horizontal, and z is height. So the right-hand rule you need to align the fingers on the right hand with the positive x-axis. Curl the fingers so they point in the direction of the positive y-axis. And then your thumb points in the direction of the positive z-axis. So as long as your coordinate setup follows this rule, then it's considered to be a right-handed coordinate system, and so it's fine. Now there is also something called the left-handed rule, which follows the exact same rules, except you use your left hand. In this course, we will only be working with right-handed systems. So that is systems that follow the right-hand rule. Now, if we take any pair of axes, we get a plane. So there are three planes in the three-dimensional coordinate system. You have the xy plane, which is taken by just the x and y axis. You have the xz plane, which is the x and z axes, and the yz plane, which is just the y and z axes. And that is shown. Much like how a point in the plane is represented as an ordered pair, a point in space is represented by an ordered triple, x, y, z. X represents the distance the point is from the yz plane. A positive value will denote that the point is in front of the plane. This means that a negative value means the point lies behind the plane. Y is the distance the point is from the xz plane, where a positive value denotes the point is to the right of the plane. So negative would mean it's to the left of the plane. And finally, z is the distance the point is from the xy plane. Positive value denotes the point lies above the plane. So a negative value would mean it lies below the plane. Now in two-dimensional space, we had 4 quadrants. In 3 dimensions, we have what are called octants, as shown here. The 8 octants are where all of the coordinates are positive. Then you can have x and y are positive, z is negative. X and z are positive, y is negative. Y and z are positive, x is negative. X is positive, y and z are negative. X and Z are negative, Y is positive. X, Y are negative, Z is positive. And finally, all of the coordinates are negative. Unlike the quadrants, there is no numbering convention with the octants, with the exception that octant 1 is the octant where they are all positive. So consider the points. P1 is x1, y1, z1, and P2 is x2, y2, z2, as shown in the figure. We wish to determine the distance between P1 and P2. Well, to do this, let's consider a third point, the point x2, y2, z1. Well, the distance between P2 and P3 would just be the absolute value of z2 minus z1, right? Because the x and y coordinates don't change, right? So the only change is in the z direction. Now, the distance between P1 and P3, well, we can treat this as the distance between 2 points in a plane because the z direction remains the same. So it's the square root of x2 minus x1 squared plus y2 minus y1 squared. Well, if we look, we have now formed a right triangle of sides, the distance between P2 and P3, and the distance between P1 and P3, where the hypotenuse is the distance between P1 and P2. Now, it's kind of hard to tell if this is a right triangle, but remember, we're in 3 dimensions. This is indeed a right triangle. Well, in that case, we can use Pythagorean theorem. The distance between P1 and P2 squared is the distance between P1 and P3 squared plus the distance between P2 and P3 squared. So squaring a square root gets rid of the square root. We're left with x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Absolute value is always positive. Squaring results in positive, so we don't need these anymore. We get the quantity of z2 minus z1 squared. We can now solve for distance by taking the square root of those sides, and we find that the distance between points P1 and P2 is the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared plus z2 minus z1 quantity squared. Well, this distance formula is similar, in fact, it's practically identical to the distance formula in 2 dimensions, except we've now had to add third coordinate because we're now dealing with 3 coordinates instead of 2. So let's go ahead and find the distance between the points 3, negative 1, 5 and 2, 1, negative 1. Alright, so distance, square root 2 minus 3 squared plus 1 minus negative 1 squared plus negative 1 minus 5 squared. So 2 minus 3, negative 1 squared is just 1. 1 minus negative 1 is 2, squared is 4. Negative 1 minus 5, negative 6 squared is 36. So we get the square root of 1 plus 4 plus 36, which is the square root of 41. So the distance between these 2 points is root 41. Let's take a look at 3 special planes. We will study planes more in depth a little bit later. So the plane in space that is parallel to the xy plane containing the point ABC can be represented simply by the equation z equals c. Likewise, the plane space that is parallel to the xz plane containing the point ABC can be represented by y equals b, and the plane in space parallel to the yz plane containing the point ABC can be represented by the equation x equals a. We now study a special surface in space. Again, we will study surfaces a little bit more in depth later, and it's the sphere. So a sphere is simply the set of all points in space that are equidistant from a fixed point called the center of the sphere. The distance from the center to a point on the sphere is called the radius. Well, this is the same definition that we had for a circle in the plane. And you should remember that the standard equation of a circle that was centered at AB with a radius of r was the quantity of x minus a squared plus y minus b squared is equal to r squared. Well, since this is the exact same definition, it would make sense that the standard equation of a sphere would be the same, except we should be adding a third coordinate. Well, let's go ahead and see if this is true. So let's consider this sphere. So it's centered at ABC, it has a radius of r, and we'll consider the point on the sphere xyz. Now, since the radius r is the distance from the center to the point, we can write r as the square root of x minus a squared plus y minus b squared plus z minus c squared. Well, now all I have to do is square both sides, and we get the standard equation of a sphere. And as we see, our intuition was correct. The standard equation of a sphere with center ABC and radius r is the quantity of x minus a squared plus the quantity of y minus b squared plus the quantity of z minus c squared is equal to r squared. So let's now go find the standard equation of the sphere with center 10, 7, 4 containing the point 1, negative 1, 3, negative 2. All right, so the first thing we need is the radius. So the radius is the distance from the center to the point. So it'll be negative 1 minus 10 squared, so it's negative 11 squared, plus 3 minus 7, so negative 4 squared, plus negative 2 minus 4, so negative 6 squared. This winds up giving you the square root of 173. So the standard equation, x minus the x coordinate of the center squared plus y minus the y coordinate of the center squared plus z minus the z coordinate of the center squared is equal to r squared. And so there's our sphere. Well, let's consider a different sphere. We have the points negative 5, 2, 3, and 3, 4, negative 1. The line segment PQ forms the diameter of a sphere. We now want to find the equation of this sphere. Well, let's find the radius. Well, since we know that the line segment PQ forms a diameter, the length of the diameter, which is d, is the distance between these 2 points. So 3 minus negative 5, 8 squared is 64. 4 minus 2 is 2 squared is 4. Negative 1 minus 3 is negative 4 squared is 16. So this is the square root of 84, which can be simplified to 2 square root of 21. But this is the diameter. Well, isn't radius half the diameter? So the radius is square root of 21. We still, however, need the center. Well, if the line segment PQ is a diameter, so if I draw it, and we'll just consider a circle for now. There's the center. And if this is the diameter, isn't the center going to be the midpoint of this line segment? So the center is just the midpoint of PQ. And remember, to find midpoint, you just take the sum of the coordinates, divide by 2. So it'll be negative 5 plus 3 over 2, 2 plus 4 over 2, 3 minus negative 1 over 2. I'm sorry. It's plus a 3 plus negative 1 over 2. So the center is negative 1, 3, 1. So our equation would be x plus 1 quantity squared plus y minus 3 quantity squared plus z minus 1 quantity squared is equal to 21. Now let's look at vectors in space. Well, vectors in space are just a natural extension of vectors in the plane. So we still have 3 notations. As a directed line segment from the initial point x naught, y naught, z naught to the terminal point x1 to y1 to z1. In component form, x comma y comma z, or as the linear combination xi plus yj plus zk, where I is the vector 1, 0, 0, so it's the x direction. J is the vector 0, 1, 0, so it's the y direction. And k is the vector 0, 0, 1, so it's the z direction. And these are called the standard unit vectors in space. And the zero vector in space is just the vector whose initial and terminal points are the same, so it's denoted as bold 0. So let PQ be the vector with initial point 3, 12, 6 and terminal point negative 3, 2. We want to express this vector in terms of the standard unit vectors. Well, we can still find it the same way. It'll be the terminal coordinate minus the initial coordinate. So we get our vector to be negative 7i minus 15j minus 4j. k. Well, vector operations. Again, since vectors in space are an extension of vectors in the plane, all of the operations and properties we studied before are just natural extensions as well. So we have two vectors, -2, 9, 5 is v, and w is 1, -1, 0. We wish to perform the following for. All right, so to start with, we want 3v plus 2w. I'm sorry, minus 2w. So this will be 3v plus -2 times w. So 3 times -2, 9, 5 plus -2 times 1, -1, and 0. Well, scalar multiplication works the same way. Just multiply each component by the scalar. So we get -6, 27, 15 plus -2, 2, 0. And the vector addition works the same way. Just add corresponding components. So we get -6 plus -2, -8, 27 plus 2, 29, and 15 plus 0. So there's 3v minus 2w. Now let's look at 5 times the norm of w. So it's 5 times the square root. Well, finding the norm of w is that's just the square root of the sum of the squares of the components. So 1 squared plus -1 squared plus 0 squared. So it's just 5 square root of 2. Well, the norm of 5w. By definition of scalar multiplication, the norm of the scalar multiple is the absolute value of the scalar times the norm of the vector. So it's just 5 root 2. Finally, we want to find EV, so we want to find a unit vector in the direction of v. So this is 1 over norm of v times v. It's the same thing. So 1 over the square root of -2 squared plus 9 squared plus 5 squared times -2, 9, 5. So we get 1 over the square root of 110 -2, 9, 5. So this is the vector -2 over, I'm not going to have enough room, -2 over the square root of 110, 9 over the square root of 110, and 5 over the square root of 110. So as we can see, working with vectors in space is no different than working with vectors in a plane. Now, as a closing comment, we can actually represent any vector in the plane as a vector in space. It's just that z coordinate would be 0. Well, that concludes the lecture on vectors in space.